Hi, I'm Alan Mincer at the Physics Department of New York University, and today we're going to do some demos of how martial artists do things like break boards to break bricks. I'm going to use boards because they're easier to break. I'll hopefully say this a couple of times while I'm talking. Don't try this at home. I'll talk a little bit during the presentation about what training does for you, and hopefully there you'll see why not being trained is not a good idea to do it. So let's start with the physics of breaking a board. Let's start by discussing the forces involved in the breaking of a board or a brick. So imagine we have a board like that, and that it's supported at the edges. What's going to happen is whatever's coming in to break this is exerting some force which we'll call B. It's very hard to shear this board, so what happens is that the board bends, and breakage occurs because of the stretching of this edge of the board, this side and that side. As this is pressed, they separate, and this causes the break. That won't happen if the board itself is exerting enough of a force upwards on this. If we think of this part of the board, if this part of the board and this part of the board are exerting enough of an upwards force to counter this breaking force. Well, let's assume this angle is theta and this angle is also theta. Then the force we're talking about in the board here is a force in that direction. So here's the angle of theta. And if we call the force of the board just F, then there's a component of the force that fights this breaking force, which we'll call the perpendicular component. And this is the magnitude of that force, and we'll call this the parallel component. And those two are related by the tangent of theta is equal to F perpendicular over F parallel. Or in order to get a force F perpendicular such that when you add the two of those together, for 2F perpendicular to be greater than or equal to the breaking force, what we get is that F parallel is equal to F perpendicular over tangent of theta. That angle theta is the same as this one. This angle is maximum if the board is breaking right before it breaks, where this is about ½ an inch and this is 5 or 6 inches. That means that this tan theta is about 1/10. You have force from this direction and that direction, both of which have an upwards component. So it says at the maximum, F parallel is going to be 5 times as big as the perpendicular force. So if this is 50 pounds, each of these are 250 pounds. Before that, let's say when you're 1/20 of an inch, these are closer to being a ton of force each. So there's a tremendous amount of force that's trying to pull this board apart for a little bit of force exerted downwards. And that's how one manages to break a board or a brick, because of this large force in that direction. Before we go on, let's look at an example of how this works. Okay, so your goal is very simple. I'm going to press down in the center, and your goal is to pull hard enough that I can press down. Okay? With me? So first I'll do this. Right? Okay, that's too easy. Okay, pinky. Okay, what's going on over here, they can't do anything because that angle is very small. As I get further and further, I could get to about there with my pinky, right? Then I have to do a little bit more, right? But for the first little bit, right, they really can't do it no matter how hard they pull, because they're exerting a tremendous amount of force, but there's only a very small component in that direction. Thank you. So we've talked about force. The next part is energy. So if we think of the board and actually whatever part of the body one is breaking the board with, say a hand is springs, right? Then when a force is applied, the spring is stretched. Somehow stretching the spring, and energy is being stored as you compress this. Energy is being stored in the body part that's hitting this at the same time it's being compressed, but bone bends much less, gives much less than wood, so the force of the board on the hand is equal and opposite of the force of the hand, let's say, on the board, but the distance the bone compresses is much smaller, so the bulk of energy goes into the board, not the hand. You need some amount of energy to break a board, and the energy carried by whatever limb is doing it is just 1/2 the mass times velocity squared. So a little increase in velocity of whatever is breaking the board will go a long way because it goes as a velocity squared. And the other part that's important is the mass. So a hand is less massive than a foot, which is less massive than an elbow, perhaps less massive than a head. So you can break with different parts of the body to get this m bigger. Now, if you successfully break it, this energy that has gone into distorting this wood or brick, whatever it happens to be, goes into breaking it. If you wind up not breaking it, but instead come to a stop, this is a spring, it just gives back the energy. And that energy therefore goes into something else, which is unfortunately the body part that went into hitting it. Okay, so if you break the board, the energy goes into that destruction and you don't get hurt. If you're not moving quite fast enough, or the mass isn't big enough, whatever this product is, if it isn't big enough, the energy goes back into the body part, and unfortunately you can break that instead. So let's talk about what training does for you. Training does not really increase the speed of any movement, right? You can do this at some speed, and pretty much no matter how much training you do, you're not going to change that. You can do this at some speed, and pretty much no matter how much you train, you can't really change that very much. But I have my leg and my hip and my shoulder and my elbow, and they're all connected. And you can imagine if I want to know how fast is my fist moving with respect to a board that's stationary here, that's the sum of all of these velocity vectors. So I have a hip vector, which let's say is that way. I have a shoulder, which is that way. I have an elbow, which is that way. I have the wrist maybe is a little bit that way. And all of these things add together to give you some component of velocity in that direction. What training does for you is help you coordinate all of these different parts of the body motion so that when you put them together, you get as large a speed in the direction of breaking the board as you can. So there are typically a couple of different ways boards can be broken. One is supported. That means you either have, sometimes you see people with a stack of bricks or something and you put boards over there, or you have some strong people holding the board over here, right? People, their arms out holding the board. So in that case, what you have is a board that's just supported at the edges. Something hits it from this side. The board is held here, so it just flexes to this position, and it eventually breaks. Oh, what's interesting is if you have a stack of boards, and you go fast enough to break some of them, but not fast enough to break all of them, then what happens is this entire thing is flexing. And what flexes the most are the boards opposite where you're breaking. So if a break is not completely successful, if it's only partially successful and breaks only some of the boards, what winds up breaking is the board, not the board you're hitting, but the board on the other side, because that's the one that's flexing the most. Let's imagine instead a situation where either the board is hanging from strings, or someone's holding the board very lightly, or someone can take a board, drop it, and just hit it. When that happens, if the board has a mass m, then there's some force being exerted by whatever is hitting it, and therefore it accelerates with an acceleration just by Newton's second law, which is force divided by mass. So if you don't hit the board, if you're not moving too fast, what you'll wind up doing is just speeding up the entire board. If you're moving fast enough, so that by the time the board as a whole picks up speed, the board has flexed enough that it's at its breaking point, then the board will break even though it's not being supported, because it's just its inertia that keeps these ends from catching up with the center. Okay, so the first thing we're going to do is supported board. So the main thing that the people holding the board are doing is keeping the board from moving so that when the limb hits it, it doesn't just push them like that. They hold it so the board has to break, right? So this is one way of hitting a board. So the idea is to hit with the fleshy part of the hand, and the idea is to put the whole body into it. Okay, so.
Wait a minute. Some kind of physics or what?
Yeah. Yes. Let's try. I'm not sure. Let's give it a whirl. Okay. Let's see. So we try with 2. Okay.
I have a question.
Yes.
How many years you practice?
35. Yes. Okay, thank you. So now the board's not supported, and as we discussed before, the idea is that if my hand is moving fast enough, and before the board as a whole catches up, the center has moved far enough that the board breaks. So as we discussed, if whatever's hitting the board is moving fast enough, it can even break it if it's not supported. And this one just requires a little bit of timing. So the goal is to go through this as it's falling. Finally, let's see what happens when you have more mass. Come. So your main goal is just to supply the pressure here so that the board doesn't move. Tell me, are you ready? Try one more.
Right.
Okay, so you've seen the physics of board breaking. For the most part, when boards are broken in martial arts, it's not a trick. There are ways to do tricks. If you take a stack of boards, it's hard to break. If you take the boards and put spacers between them, and sometimes you see that done, then it's a lot easier because each board is breaking individually as opposed to the whole thing flexing. But in general, there's physics to this, right? It really happens, and please don't try this at home.